introduction. Thank you very much to all of you for attending my talk. I would like to show you the next about 20 minutes, which is a challenge. Work that we have been doing over the past few years in my lab in mechanical engineering and material science department here on the topic of solar-powered hydrogen generation. In more scientific detail, it would be how we study heat, mass, and charge transfer on nanoscale structures to drive thermally chemical reactions, catalytic reactions. And the one that we are most interested in this case, is how to produce hydrogen. Hydrogen is an economically very important product. It is used in many industrial large-scale applications like fertilizer production, and it has the potential to be a very nice, clean, efficient fuel. Toyota did me a great favor a few months ago by presenting their hydrogen-fed fuel cell car. It's called Mirai, I hope I pronounced it correctly. And I'm not paid by Toyota, but I will mention it a few times, because it is a great application that shows that fuel cells and hydrogen can actually be used in real applications. That Mirai should be available commercially in the US in this summer, I believe. So it's an actual device, not only an idea. What most people don't know, if you use or you want to use hydrogen in your car or anywhere else, today almost all hydrogen worldwide is produced by steam reforming. So you take a hydrocarbon fuel and convert it to hydrogen at high temperatures. Methane or natural gas, which is a cheap source of hydrocarbon fuel for this, requires something like 700, 800, 900 degrees Celsius. To get up to that temperature, to heat up your fuel, your water, and provide the reaction enthalpy, because it's an endothermic reaction, you need a lot of heat. And industry does that today by burning around half of the primary fuel. So we say that's a waste if you have to burn half of the fuel to react the other half. That's especially important if you want to work with ethanol, methanol, or other biomass-derived fuels, biofuels, as we want to do it. They're more expensive, they're more precious, so we don't want to burn half of them to react the other half. Everything that I'll show you today is related to methanol, simply due to the fact because it has the lowest fuel reforming temperature of any hydrocarbon fuel or alcoholic fuel. We want to go to other, probably more interesting fuels in the future. So our idea, our vision for the future is to use an easily transportable and storable fuel, like for example alcohol, convert it to hydrogen with the help of sunlight, and then convert the hydrogen in a fuel cell to electricity. A small-scale, decentralized power plant, basically in your single-family house or office building, something like that. We can store some of the hydrogen, but the idea is to only store it intermediately, small scale. We don't want to have the kind of heavy, bulky hydrogen tank, or in my lab we call it hydrogen bomb, that Toyota puts into their array. We store most of the energy in form of alcohol, which is very safe, very cheap and easy. But we can store the sunlight in form of hydrogen for the night, or in short term, if you like. So this is with a bit more technical detail, the same idea. We convert methanol or other fuels with water by steam reforming under sunlight to hydrogen. One problem with any fuel reforming reaction is that in any fuel, you will produce a small but significant amount of CO. For methanol, it's around 1%, which is not a lot, but since CO, carbon monoxide, is very toxic, we would destroy low-temperature PEM fuel cell catalysts within minutes with 1%. So we have to reduce that amount drastically. We use preferential oxidation to do that. We can then store in a compressed or non-compressed form the hydrogen intermediately if you want to, and then use it in a fuel cell whenever we like. We have capabilities in my lab to produce a lot of nanoscale catalysts. For example, we use flame stir pyrolysis. We use these copper oxide, zinc oxide, aluminum oxide particles around 10, 15, 20 nanometer in size that give us very high methanol conversion. For example, we could show here that with 65 to 8% copper oxide content, we have full conversion of methanol at around 250 degrees Celsius. That is important because we want to drive this chemical reaction entirely heated, only heated by sunlight. So we build our own solar collectors, solarthermal capture devices that look like conventional flat plate solar collectors that you might know. But we want to run this one without concentrating, without focusing the sunlight at 250 degrees Celsius, which is roughly 100, 120 degrees Celsius higher than any commercial product can do without focusing the sunlight. If we want to in the future focus or concentrate the sunlight, we want to be able to go into higher temperatures and not only reform methanol to hydrogen, but as well other more interesting fuels. This 250 degrees Celsius non-concentrated solar collector is very interesting to us because it's very new in the sense that it doesn't fit into either of the two dominant solar thermal devices or systems that are available today. You probably know these non-concentrated, simple, very cheap, low complexity systems that heat up water. For example, in North Carolina, you can find them on many houses. Very cheap, but all they do is they give you 50, 60, 70 degrees Celsius hot water that you can use for a shower or to heat your house, but you cannot run a power plant with that. On the other hand, these highly concentrated systems, solar systems, CSP systems, that, for example, use acres full of mirrors, focusing all the sunlight on a small area, they can give you high temperatures. You can thermally split water at that temperature or run a gas turbine with it, but they're very big, they're very complex, they're very expensive, and you will not be able to scale that down and put it in your backyard in a small decentralized power system. So we want to do something in between, ideally have a temperature closer to adapted to, not 1,000 degrees Celsius, but at least a couple of hundred degrees Celsius, but still use the materials and the systems and the designs closer to these very cheap conventional non-concentrated systems. The way we do that is we take a highly selective absorber coating, place it on a copper plate with a copper tube. In terms of how it looks like, it's a very conventional flat plate zone collector, but we use very good contact methods, connecting the selective coating to the collector. We use a very good selective absorber coating. We put it in a vacuum chamber with a very good vacuum. This chamber is very big, but that's only due to our experimental requirements. In a realistic device, you would make that vacuum chamber much smaller, just surrounding the collector. And if you then shine our artificial or real sunlight on it, we can actually achieve temperatures up to 27 degrees Celsius without flowing any fluid through. If we pump water methanol, liquid water methanol at room temperature through the system, we can still achieve easily 250, 240 degrees Celsius, depending on our flow rate. That is high enough to convert on our catalyst, that is inside of the collector, all the methanol that we pump through up to flow rates of around 4, 4.5, or 5 milliliter per minute square collector area. Now, a few milliliter per minute liquid water methanol doesn't sound like much, but if you look at the amount of hydrogen we can produce with that, there are two different reactor sizes or amounts of catalyst. Our larger one inside of the collector, we can produce around 6.5 liters, about 2 gallons of hydrogen per minute square. That's a significant amount of hydrogen. And that's especially significant if you look at how much energy that is worth. That has a lower heating value of around 1100 watts per meter square. Which is pretty nice because we put in one sun, 1000 watt meter square sunlight, and we get 1100 watts hydrogen out. We have a solar to hydrogen efficiency above 100%, which is not cheating. We can of course only achieve that because we have fuel, but the input of energy in form of fuel, methanol, and sunlight is about half-half. So more than 100% efficiency solar to hydrogen if you connect that to a very standard off-shelf PEM fuel cell, low temperature fuel cell, 50-60% efficiency easily, hydrogen to electricity. This solar collector and catalyst connected with the fuel cell to give us easily 50-60% solar to electricity efficiency. If you add the methanol, we will be somewhere around 25 to 30%. Now, one problem with this methanol steam reforming, any steam reforming, as I said, is you produce a small but significant amount of CO. If you want to be able to connect your on-board or small-scale fuel reforming with a PEM fuel cell that has a low tolerance to CO because of its platinum catalyst, you have to be able to get very efficiently rid of almost all of the CO. Already in the 80s, researchers, for example, Japanese researchers have shown that very small, ideally below 10 or below 5 nanometer sized gold particles are very efficient in oxidizing CO without oxidizing much of the hydrogen, which is your fuel you don't want to waste. But the problem is that if you have CO2 and water in your gas mixture, none of those catalysts work well. And they have to work very well. If you want to go from 1% CO in the methanol steam reforming to the tolerance that a PEM fuel cell has, it's maybe 10, 15, 20 ppm, we need at least 99.85, 99.9% CO conversion. That's a very high conversion rate, and it's very challenging. CO2 and water you will have intrinsically in any fuel reformed product gas. So industry has found ways to do that with different catalysts at high temperature, like 200, 250, 300 degrees Celsius. Water gas shift reactions are pretty big and complex. If you want to do it in a small system, none of those will be affordable. So what we do is we try to do PROX, preferential oxidation of the CO, on a catalyst that is able to do it even if you have CO2 and water in your gas mixture. And when we started this work, nobody actually really looked much at the iron oxide, which is the support of our gold particles. People made huge, in our standard, micro scale iron oxide particles and added these small gold clusters on top of it. And we started to think that probably the problem is not the gold that everyone focuses on, but the size of the iron oxide. So we turn it upside down and produce these so-called inverse catalysts, where our primary catalyst is actually relatively large. The gold is around 15, 20, 25 nanometers, but the supporting quote, of iron oxide surrounding it is actually much smaller, 5 to 7 nanometer in diameter. And we could show that we apparently were right. The main limiting factor, if you have CO2 and water in the gas mixture, is not the oxidation of the CO, but actually the adsorption and the transfer of oxygen to the interface between the gold and the iron oxide here. If we increase the surface area by making iron oxide smaller, we can have much more oxygen being absorbed and transferred to the interface. And due to the lack of time, I don't want to go into too much detail, but we were able to achieve full conversion of CO at 70, 80 degrees Celsius, even with high amounts of CO2 and water from the gas mixture. Only if you have excessive amounts of water, above 10%, we cannot fully convert all the CO, but otherwise we could. And this is, again, unrealistically high. And if we add both CO2 and water, again, the same story, at 70, 80 degrees Celsius, which is typical PEM fuel cell temperature, we could convert 99% of the CO in our gas mixture 70 degrees Celsius. So we showed here a method to easily connect this PROX with fuel refineries that we would do before that, and a fuel cell into one system. And that's what we're working on right now, to connect these two together. So since I have only 5 minutes for the second part of the talk, so this is the proof that we do not deactivate our fuel cell with the CO. We can run it for hours if we connect a PROX reactor that cleans out the CO out of our dirty fuel before we feed it into the fuel cell in one integrated system. So I skipped the conclusions of this. That's everything we've shown you so far, and go to the second part. A problem that we have with this system that I showed you before is that we need a relatively large surface area to absorb enough sunlight to heat it up to the temperature we need to drive the chemical reaction. So but our catalyst is nanoscale. So all that we want to heat is the catalyst in nanoscale and maybe its surrounding to heat up the fuel, the water, and drive the chemical reaction. So we were thinking, is there any way to in nanoscale heat a catalyst without having to heat the whole bulk of our collector and the reactor? And talking with Dr. Tony Modini from the biomedical engineering here, he said, well, what you're looking for is plasmonics, or local surface plasma reactants, where for example, in this crevice between microspheres, you have nanoscaled curvatures, radii, where the surface electrons in a resonant way interact with photons hitting them, and in very local scale generate very high electric fields. And we were hoping that those mean high light absorbance and, for us, high temperature, so that we can drive the chemical reaction down here without having to heat the rest of the system. And we were very happy that last year and this year again we could get coming from Dr. Noel's energy initiative to test this. I skipped the literature review. Before we started this work, people have shown that you can use plasmonic structures to heat water, for example, to 140 degrees Celsius. And the last 2 or 3 years, more and more people have studied plasmonically driven photocatalysis, where all the chemical reactions that I show here are electron driven. For example, similar to water splitting. But only one study has shown before we started this work that you might be able to thermally drive a catalytic reaction for heat, not for electrons, not for take in some way. But this study was only able to do that at concentration ratios of, this corresponds to 700, 800, 900 times. So you need very high concentrations, they needed very high concentrations to thermally drive through plasmonics a catalytic reaction. This is unrealistically high in our opinion. We cannot make a real device of that. So we use these nanowave substrates that have these half micron polystyrene spheres. Our collaborators coat them with gold and see in common solid simulations that we have about 8 times magnification of the electric field in the crevice of 2 of those hemispheres. And we now add the catalyst on top of that, so this is polystyrene spheres, and with the gold coating that makes them plasmonic. we add in this rough surface on top there, that's our catalyst. And the main good news is we could see the generation of gas bubbles. So for example, here within 2 seconds, you can see 2 different bubbles being generated. We analyzed the gas that we produced there, and it was 3/4 hydrogen, 1/4 CO2. So apparently we have on this pool of methanol and water liquid the generation of gas that corresponds to methanol steam reforming. But the whole substrate here, the whole pool of liquid in our whole reactor is cold. We have temperatures that are below 30 degrees Celsius, so we are not heating in any substantial way the whole reactor in bulk. But apparently we are able to locally heat it enough to drive methanol steam reforming. Our gas production is pretty low, but that's mostly because we only have very small areas where we can actually have a plasmonic effect due to the structure of our plasmonic substrate. These microspheres are relatively large, so only about 1% of our area is actually able to feel the effect of this plasmonic sphere. There are many plasmonic structures that don't have this large structure, and are smaller and can feel the plasmonic effect every bit, so that's where we want to go in the future. But most importantly for us, if we take this small area that we can only use actively into account, we apparently generate temperatures above 200 degrees Celsius, around 220 degrees Celsius, if we back calculate the amount of gas that we produce with our known catalytic reaction kinetics. So we have, without heating the whole substrate, apparently locally in nanoscale temperatures above 200 degrees Celsius that are high enough to drive methanol steam reforming. Since we don't have to heat up the whole bulk of our liquid pool, of our substrate, of our whole reactor, we have virtually none, very small heat losses in our system. So we hope that with this we can make it much more efficient. Well, I forgot to say the number before. We need to concentrate the sunlight for that, but only in a moderate amount, but 12 times. The only study that we know, as I said before, that could do anything similar to this needed 800, 900 times concentration. So thank you very much for your attention, and thank you very much to my agencies and all the students that did the work actually.
Questions? Can just because you say local temperature, can you say how local that temperature is? I mean, which subsystem or? So
we have not been able to measure that in our specific system, but from these kind of substrates, we know from our collaborators that what I call here the plasma propagation length, kind of how wide, how far away you will feel that plasmonic effect, it should be in the area of 5 to 10 nanometers. Okay. And depending on that, which again we have not been able to measure yet because it's kind of small, we have around 1%, near 1% active in the area. And that brings us back to that temperature of 220.
On the same matter, could you allude to what active area you would need to reach to have a feasible amount of hydrogen production?
Well, so if you use particles, structures that are in this 10, 20 nanometer range, you would basically have the whole area of your sphere, or our collaborator has nanostars, sounds even cooler. Nanostars that are basically active everywhere. In that case, we would have, if you look at 1%, an order or 2 orders of magnitude more gas production, more plasmonic active area. The second thing is we only have one structure size in this system right now here, which means we only have one resonance frequency, meaning the range of the light that actually triggers this plasmonic effect is relatively limited. We think it's around 80 to 100 nanometers in the wavelength spectrum. So if you use different structure sizes, we can broaden that range drastically, and if you use smaller structures, we can use more or almost all of our area. That together should give us around 3 orders of magnitude more gas production, we hope. And with that, we will be better than my very applied system that I showed you before. But this is very far away from any application yet and very fundamental research.
Okay, if there's no other questions, let's thank Nico. Thank you.